So, everyone knows the importance of auto-scaling. It's about adding resources at the right time so you don't have to over-provision for the peaks and waste lots of money, but can scale when you need to. So it's a balancing act. You want to have enough resources to be reliable, but not so many you're inefficient. And then on Kubernetes, there's typically 3 dimensions of auto-scaling people think about. So first is the cluster. So you want to have a whole bunch of containers, you run them on nodes, and you need something which is going to add nodes to schedule new containers and remove nodes when they're not needed. So that's at the top, that's cluster auto-scaling. And then at the workload level, then you can, so you have 2 options. Sorry, Rafa. So there's 2 options. You can scale horizontally. So this is, you have replicas, you add replicas to scale up, you remove replicas to scale down. And then you can scale vertically, which is, okay, I'll have the same number of replicas, but I can make them bigger to have more resources, etc. And then for each of these dimensions, there's a few different tools. And typically there's a sort of more established tool which has been around since the beginning of Kubernetes, HPA, Cluster Autoscaler, VPA, and then a few more advanced tools which came up in the last few years, KEDA, Karpenter, etc. So we're going to do a sort of whistle-stop tour and go through the different sort of how it works, challenges, etc. So I'm going to start with horizontal because that's where most people start. And the idea is you get spikes in traffic, how would I respond to that? So the Kubernetes, if you run any Kubernetes cluster, there's an object called the HPA, the horizontal pod autoscaler, and that will manage the number of replicas you have automatically. And then the way it works is Kubernetes has a metrics server. That's the backbone of the sort of monitoring metrics used internally by Kubernetes. The kubelet will be pushing usage data for all of the different containers running on that node to the metrics server, and the HPA will be constantly querying that to see what's being used. Once it makes a calculation, okay, this needs more replicas, less replicas, it will patch whatever workload that HPA is managing, and then once that is patched with the replicas, that workload is then responsible for spinning up or down the new pods. So it'll work differently for a deployment, stateful set, etc. And so it's pretty simple from an engineering point of view, but the more interesting part is, okay, how is the calculation which is going to control how many replicas I get? So a little history of the HPA. The first version of the HPA which came out was based, the only thing it supported was scaling on CPU utilization. So if you were to look at this, you would see usage, requests, and then how they evolve with time. You can see the first line, there's very little utilization, a load spike comes in, CPU usage goes way up, far above the target utilization that the HPA is trying to maintain. The HPA will see that, will add a new replica, you see the second one come up, and it will share the load between the 2. And then what it's doing all the time is just looking at the current utilization and the target utilization and adding replicas so that basically the utilization matches the target. So this worked great for lots of situations. However, the issue people frequently run into is the CPU utilization is often not a very good proxy for the load on a workload. If you have something which is very bursty or something which is doing a lot of network I/O, so it's waiting a lot even if it's under load, you can have issues. So this plot is from a KubeCon talk. I have a link at the bottom. This is showing the replicas over time for a workload. It's a company called Acquia. They host Drupal. And the huge change was when they cut over from scaling on CPU utilization to scaling on a custom metric coming out of their web server. Basically, how many available workers were left in the web server. And what they found was when they were scaling on CPU utilization, it was very erratic and noisy, and constantly adding and removing workloads wasn't helping them scale at the right times and was just wasting a lot of money. And you can see afterwards how stable it is and how it still is able to scale up and down as needed. So if you can, scaling on a custom metric is way better if you can find one which works for your workload. And V1 of the HPA supported just CPU utilization. V2 of the HPA supports basically anything. So you can scale on custom and external metrics. You can scale on multiple metrics. You have fine-grained policies to say, okay, if I scale up, don't scale down for 10 minutes. You can do basically anything, which gives people a lot of power. However, the issue is managing all of that plumbing yourself gets really, really painful. So there's another tool, KEDA, the Kubernetes Event-Driven Autoscaling. And what it's trying to do is provide a layer on top of the HPA to simplify all of that. And it comes with a whole bunch of pre-built scalers. So at StormForge, we have a machine learning task queue. We scale on the depth of that task queue. When there's lots of jobs to be done, we scale up. When there's not, we scale down. We do all that with KEDA pre-built scalers. So integrations with common tools like RabbitMQ, cloud provider specific ones like SQS from AWS. It also provides a whole bunch of built-in authentication providers because you need to be able to talk to different tools. For example, we scale on a message queue hosted by Amazon, so we need to be able to authenticate to it. A big differentiator is it also supports scaling to zero. So if you have batch workloads which can actually be scaled to zero, you can save a lot of money. And then it's extensible. Like many things in the sort of Kubernetes ecosystem, you can build your own. So the idea is you get all of the benefits of scaling on custom metrics, etc., without having to manage all of the authentication, data plumbing, integrations, etc. It all comes out of the box, totally turnkey. And we've seen lots of people use it, and they use it to great success. So that's everything on.
Yeah, actually, this mic, I think it's a little bit louder than the other one, so maybe we can, or I am louder, that can be the reason as well. So if we're scaling pods, we can use like any type of tool, so HPA, KEDA, doesn't matter. We need to scale then, but we need some place to place those pods, otherwise the pods will become in pending state forever. So there are some options that we need to have, enable and deployed in our cluster to be able to scale our nodes and to be able to host all those new pods that are coming up. Doesn't matter if you're using KEDA, if you're using HPA, you're gonna need to have capacity for them to come up and be launched in your cluster by the scheduler, which comes with the first option that we're gonna introduce for you today, with Cluster Autoscaler. How many of you here use Cluster Autoscaler in production today? Awesome, there are people who use like Cluster Autoscaler in production, so I think by now you should be pretty familiar on how the autoscaling logic works. So first we have some scaling mechanism triggering it, so that could be either KEDA or HPA or whatever you're using, Prometheus metrics, external adapters like John was saying. Then those pods will come in pending state. So HPA changed your replicas from 1 to 4, doesn't matter. 4 pods in pending state because you don't have capacity. Then you have Cluster Autoscaler installed in your cluster. Cluster Autoscaler by itself doesn't provide any nodes. What we need to give to Cluster Autoscaler then is an autoscaling group, right? In this instance of AWS, we call that autoscaling groups. And then it's up to the autoscaling group, once we change the desired amount of instances, to then provision that instance for us, right? But there is a specific pain point here that a lot of my customers face. That is, each node in a node group must have identical scheduling properties. So by that I mean you need to use the same amount of CPU and memory for all the worker nodes that you have in an autoscaling group. And why is that? Because since Cluster Autoscaler just changed the desired amount of instances in an autoscaling group, it doesn't know which instance to pick based on your workload. So it doesn't take in consideration the amount of resource requests you are defining for your application. You just know that it needs to launch a new node using the autoscaling group. So with that in mind, knowing that we need to have a node group with identical scaling properties, it's fine. We have just one node group. We're using M instances. Now we have another one using R instances. Now we need a GPU one because we need to support GPU use cases. But you know what? We are not only reserved to on-demand instances, John. We also need spot instances for all those node groups as well, because we cannot have spot mixed with on-demand in the same node group with Cluster Autoscaler. So this is basically me and Cluster Autoscaler when I'm dealing with that situation. The more node groups that I see, more I think about Kubernetes upgrades. Kubernetes upgrades. It's almost like a mantra. So we need to be able to improve that a little bit, right? And also the Cluster Autoscaling doesn't consolidate the nodes so well, so we can further do a better optimization with different mechanisms. And that leads me to Karpenter. How many of you use the Karpenter in production? Awesome. So there are people who use Karpenter in production. But essentially, Karpenter was built by AWS, but then was donated to the community. Now we have different cloud providers building on top of Karpenter. Azure, if I'm not mistaken, I don't remember if Google has as well, but it started at Amazon. And the difference between Cluster Autoscaler, I'm going to dive deep into the diagrams, but the main difference is Karpenter will take your resource requests of both CPU and memory in consideration when provisioning the nodes for you. So instead of just changing the desired amount, it will actually do an application first scaling. This is what we call in Amazon. So it has rapid scaling. I'm going to show in a demo how fast it is. But if you compare to Cluster Autoscaler, folks that use it, it can have a node up and running in less than 25 seconds. So that's pretty rapid compared with Cluster Autoscaler. It's open source, so people can contribute, can help, can improve the features of Karpenter, and we are consistently launching new features. And of course, as one of my favorite features, is automatic consolidation. So how Karpenter works, Cluster Autoscaler works that way, as I told you before, right? Cluster Autoscaler, autoscaling groups, EC2 APIs. What we are doing with Karpenter is we are removing those two agents in the middle and replacing that with a Karpenter controller. And essentially, what Karpenter controller does is it will receive the amount of pending pods, it will look into those pending pods, it will sum up the amount of resource requests for CPU and memory, and then it will provision the best node for you in that very time. And then you could be asking, how Karpenter knows which node to provision? It's because we have a concept of node pools that we can define multiple instance types. So essentially, Karpenter sends a message to the EC2 Fleet API. I don't think I'm changing that in the slide, but is it to the EC2 Fleet API just with the properties and say, pick the best instance for me. And then it's up to the EC2 Fleet API to then launch the instance. Could be a different instance than what Karpenter originally requested, but it's the best instance that satisfies that workload in that very time. So how Karpenter scales, basically we have a bunch of pending pods, HPA, whatever. Karpenter will look into those pods, sum up the resource requests for memory and CPU, and then provision the best node for you. As you can see here, the scheduler schedule pods in additional nodes that were not provisioned by Karpenter, but there's a new node coming as well. But Karpenter can also consolidate. So essentially, what Karpenter can do is provision a bigger instance and move workloads around to consolidate into smaller instances. So as you can see here, Karpenter told the nodes to be drained, and then those pods were placed in the new node with capacity. So we consolidate. Another thing that Karpenter can do is, okay, I have two nodes here. What I can do to remove those nodes? How I can improve the cost optimization of my environment. So Karpenter is able to base it on a scale-in event, let's say. You have removed some pods. Karpenter knows how many pods it's running, and then it will launch a bigger node, and basically will deploy those pods into that bigger node, consolidating even further for you. Of course, all that is customizable. You can opt for consolidation, not for consolidation, depending on the workloads that you are using. But this is a huge benefit that Karpenter provides to customers, the ability of consolidate. Maybe if you are talking about GPU instances, who are very expensive, that could be a way to save money. So a segue to that is spot instances. So if you want to have a way to actually save money, Karpenter can help you in utilization of spot instances. But you could be asking, but AWS just give me like 2 minutes warning when I'm dealing with spot instances. Luckily, with the node pool and Karpenter, you can configure different options. You can pick spot and on-demand, and Karpenter, based on your preferences, will launch the best instance for you. Usually using a mechanism that we call price capacity optimized. So it's going to try to find the instance that has the less probability of being interrupted and launch it for you. One thing that is good and Cluster Autoscaler doesn't do is, if it doesn't find a spot instance in that very moment, it can fall back to on-demand instances. So we know with spot, we have up to 90% price optimizations. Of course, not with every instance. Sometimes we're not going to be able to launch like GPU instances because they are higher requested and required. So the advisory that we give is, I'm not going to go to a meeting now. Let your Karpenter pick the best instance for you, but then we need some other stuff configuring our workloads as well, and John is going to take us away from that. So here I have a quick demo. It's actually really quick. Let me just put in entire screen here. There we go. So everything starts with a cluster. So we have an EKS cluster. We created that EKS cluster with Terraform, pretty standard. Here we also have managed node groups. Why? Oh. Why is that? Because Karpenter cannot manage its own nodes. So we need to deploy Karpenter somewhere. Okay, it's not going to work with a spacebar. I'm going to be clicking on the demo. So we need a managed node group to install Karpenter. All right, and in that managed node group, we are applying a taint. So just the Karpenter controller tolerates that taint and is going to be scheduling that node group. So we are installing Karpenter using Helm shards in Terraform, pretty standard. So let's take a look in the terminal and what it looks like actually. So we have an EKS cluster up and running. We have 2 nodes that we defined in the managed node groups, as you can see right there. And then we have Karpenter controller running as a pod in the Karpenter namespace. All right, so we have two pod controllers running. One is a passive, one is active. And then we are going to now see the Karpenter logs, because that's going to be important for us because we're going to be launching nodes. So let's just take a look at the Karpenter logs. Okay, that's fine. Let's put the logs up so we can see new nodes coming up. And now what we're going to do is we are going to provision Karpenter based on this EC2 node class and node pool configuration. I'm using BottleRocket for that. And in the node pool configuration, I want to highlight 3 main things. One, the instance category, as you can see here, is pretty broadly, so I'm not specifying any other, like C4 specifically, I'm giving C, and then I'm specifying the capacity type as being on demand. I could use a spot, and we're going to do that at the end of the presentation as well. Another thing I want to highlight is the disruption mechanism that I was showing for consolidation. So this is when empty and underutilizing, it's going to consolidate after 30 seconds when realize if it's empty or underutilized. We're going to be seeing that during the demonstration. So what I'm going to do now is basically show the node pools. So we already have that node pool that I just showed it to you created in the cluster. And now what we're going to do is we're going to go to the pod that we're going to deploy. So we are going to be deploying 2 pods, one CPU intensive and one memory intensive. And then we're going to show Karpenter scaling up, doing the consolidation, and doing all the good things that I just talked to you about. So that deployment, as you can see, has a higher CPU to memory ratio. So therefore, Karpenter will probably spin up C instance types because of the higher vCPU to memory ratio. So what we're going to do is we're going to get the pods under the phone namespace in the screen right here. In the other screen, we're going to use an open source project called EKS Node Viewer using a label called Karpenter node. So we just see the nodes related to Karpenter. If you look at the node pool right now, you're going to see that I'm applying a label here as well. So we're going to pick up the nodes just related to that label, and then we can see how fast Karpenter scales up. And then what we're going to do now, we already have the deployments deployed, but they are with 0 replicas. I'm going to increase the CPU intensive one to 3 replicas first. Of course, it's a little bit speeded up because essentially I don't have a lot of time here in the stage today, but the entire demo took 11 minutes. I speed it up to take like 5 minutes. So it's not, but you can see by the time, the amount of time that Karpenter took to spin up that node for you. So we already have a new node up and running, and trust me, you can try yourself. You will have a node in, on average, 30 seconds. So now what we're going to do is we're going to go to the memory intensive one, and we're going to do the same thing. It has a higher ratio of memory to vCPU, so we're going to scale that to 3 replicas, and it cannot fit in that node. So what Karpenter will do, it will provision a different instance type for you based on pending pods. So we have pods in pending state, Karpenter triggers the provisionment, we have a new node up and running, M6G instance, and now the scheduler will scale all those pods in that M6G instance once it's ready. So now we have the pods up and running, but as you can see, it's a little bit imbalanced because the CPU is not being fully utilized in that node. So what I'm going to do now is scale the memory intensive to 10 replicas. Scaling that up to 10 replicas. 10 replicas, additional 7 replicas will show up. And as you can see, we already have a new node coming up that has support for that additional replicas that we asked the deployment to provision for us. So as soon as the node becomes ready, the scheduler will then place those replicas into that node for us. Okay, so it's ready, now it's running. And what Karpenter is going to do now is, hey, I think I have a lot of capacity in that node in the bottom. So maybe I can consolidate my workloads a little bit, and that's because of my consolidation configuration that I have here on the disruption. So when empty or underutilized, that's absolutely underutilized. So Karpenter is deleting it. It moved the pod around to the other node already. But again, R6G 2x large is too big. So what Karpenter can do is, it will notice that, and it will start to consolidate into that other node. So we're going to reduce the costs, but at the same time, maintaining all the replicas that we have in our environment. Of course, Karpenter will take in consideration pod disruption budgets, affinity, anti-affinity rules, pod topology spread constraints. All that is taken in consideration as well when you ask it to scale the nodes for you. So now we have a consolidation happening. There we go. We have just one node now with all the pods. And then, but we are using on-demand capacity, right? And that's costing for us $294 a month. I told you that we could use a spot. And by the way, since this is a list, it could be either spot and on-demand, and it would use the logic that I told you before. But let's just switch that to spot and apply the node pool. Once we apply, we're going to see in a few seconds Karpenter scaling a new node based on spot capacity, and then shifting your workloads from node A to node B as soon as it's in ready state. There you go. So now the workloads are being shifted. The instance that was on demand, it's going to be terminated. So from $294 a month, we go down to $169 a month for the same amount of workloads, as you can see here in the screen. But in order for Karpenter to work well, right, John? In order for Karpenter to work well, we need to make sure that our pods are right-sized, right-profiled. Otherwise, it's going to scale, and that's pretty much it.
Yeah, exactly. So as Lucas said, the way Karpenter picks the right nodes to balance cost performance is by looking at how many resources those pods request. If you request a lot of CPU, you get a CPU-heavy load. You request a lot of memory, you get a memory-heavy node. However, the dirty secret of Kubernetes is people are horrible at setting these values. So I think Jonathan showed this earlier. 50% of containers use less than a quarter of the resources they request, and then the other 50% are as likely to be under-provisioned and risky as they are to be like the right size. So people do a terrible job of setting this. And so the reason they do that is, first, they ignore requests. That ends very quickly when they have an outage. Then people start doing a one-size-fits-all t-shirt sizing. They just say, okay, I'd rather be expensive than unreliable and give everything way more resources than it needs. And then people try to do it manually, but it's just very, very difficult to do this at scale. If you have thousands of workloads, you're not going to manually right-size them all on a regular basis. So people just live with a lot of inefficiency and over-provisioning. So there is a tool, the VPA, in the community to solve this. It's not used anywhere near as much as the HPA cluster autoscaler Karpenter for a variety of reasons. A big one is it fights the Kubernetes HPA. People struggle trusting the recommendations, configuring it to give right recommendations, etc. But the company I work at, StormForge, we have a way to do this automatically. So we discover all the workloads in your cluster, and we pull all the metrics straight out of Kubernetes, make recommendations, you can see them, and you can see what you would save. And then we also have the automation once you're ready to roll it out at scale. And we typically see people save 50, 60, 70%. And then the other tool we wanted to talk about briefly in the space, which came out at reInvent a few months ago, is EKS Auto Mode. So just like with StormForge, the idea is there's all these manual tasks that you don't want to do. When Lucas was doing the Karpenter demo, he had to do a lot with provisioning the cluster, installing Karpenter, taints, tolerations, configuring the node pools, etc. So EKS Auto Mode, the idea is to provide clusters which take all of this off your plate so you can focus on just running your workloads. So it will manage the installation of Karpenter, upgrades, everything. And we've seen from the people we speak to, people are super excited because people want to focus on the stuff which matters to them and not just spending tons of time administering the clusters. So I'm getting the time to stop sign. They're going to play me off. We have a booth. Come find us at the booth. Come find us at the happy hour. And if you want to talk about any of the above, Karpenter, KEDA, Automode, etc.
Gen AI.
Lucas wants to talk about Gen AI.
That's it. Thank you so much, folks. I really appreciate you.
Thanks.